Welcome to Software Architecture, Lecture 5, Availability. This is your Professor Atif Fareed Mohammed. We'll discuss in this lecture what is availability general scenario, tactics for availability, a design checklist for availability, and then we'll summarize this together. So what is availability? Availability refers to a property of software that there are ready to carry out its task when you need it to be. This is a broad perspective and encompasses what is normally called reliability. Availability builds on reliability by adding the notion of recovery, also known as repair. Fundamentally, availability is about minimizing service outage time by mitigating faults. Let's look into this using a use case. Let's look into this in a hypothetical town of Techville. There was a university named Techville University, like Technology Village. The university was growing rapidly, and managing everything from student enrollments to class schedules was becoming a big challenge. The university staff was overwhelmed with paperwork, and important information often got lost or mixed up. They realized they need a better way to manage everything, so they decided to build a university management system. Imagine this system as a big digital helper that keeps track of everything happening at the university. It is like a super organized friend who never forgets anything. This system would store information about students, teachers, classes, and even events. For example, when a new student named Alex enrolls, the system would create a profile for Alex with all his details. It would also help Alex sign up for classes and keep track of his grades. Professors could use the system to plan their lessons and share homework assignments with their students. But the best part is how it makes everything easier for everyone. Students like Alex can log in to see their class schedules, submit assignments, and even check their grades without having to ask their teachers. The teachers can manage their classes more efficiently, and university staff can handle administrative tasks with just a few clicks. This way, everyone has more time to focus on what's really important: learning and teaching. The university management system become the backbone of Techville University, helping it run smoothly and grow even more. Availability general scenario. The portion of scenario is source, stimulus, artifact, environment, response measure. The possible values in terms of source, internal or external, people, hardware, software, physical infrastructure, physical environment, as we just discussed in the university management system. The fault, the stimulus is fault, is omission, crash, incorrect timing, incorrect responses. The artifacts are systems processors, communication channels, persistent storage, and processes. The environment is normal operation, startup, shutdown, repair mode, degraded operation, overloaded operation. Response, prevent the fault from becoming a failure. Detect the fault, log the fault, notify appropriate entities, people, or systems like tech support and all that jazz. Recover from the fault, disable source of events causing the fault, be temporarily unavailable while repair is being effected. Fix or mask the fault, failure, or contain the damage it causes. Operate in a degraded mode while repair is being effected. In terms of response, measure time or time interval when the system must be available. So between 9 a.m. to 5 p.m., for example. Availability percentage is 99.999%. Time to detect the fault, time to repair the fault, time or time interval in which system can be in degraded mode. The proportion, or 99%, or rate example is up to 100% per second of a certain class of faults that the system prevents or handles without failing. Sample concrete availability scenario. The heartbeat monitor determines that the server is non-responsive during normal operations. The system informs the operator and continues to operate with no downtime. Let's look into this with a use case. Let's carry on with the Techville University, the city of Techville. The university's IT department was responsible for keeping the computer systems running smoothly. One of their most important jobs was to make sure that the university's main server, which stored all the important data and applications, was always up and running. To help with this task, they used a special tool called Heartbeat Monitor. The Heartbeat Monitor was like a digital doctor that constantly checked the server's pulse. It sent regular signals to the server to see if it was responding normally. If the server was working fine, it would send a signal back, letting the monitor know that everything was okay. This process happened so quickly and quietly that no one even noticed it was happening. However, one day the heartbeat monitor detected something unusual. It sent a signal to the server, but there was no response. The monitor waited a moment and tried again, but still there was no reply. The IT team immediately knew something was wrong. The heartbeat monitor alert system kicked in, notifying the team that the server was non-responsive. They quickly sprang into action, checking the server's connection and running diagnostic tests to find out what was causing the issue. Thanks to the heartbeat monitor, they were able to identify and fix the problem before it caused any major disruptions. This ensured that the university's system remained reliable and that students and staff could continue their work without interruption. The goal of availability tactics. A failure occurs when the system no longer delivers a service consistent with its specification. This failure is observable by the system's actors. A fault or a combination of faults has the potential to cause a failure. Availability tactics enable a system to endure faults so that service remain compliant with their specifications. The tactics keep faults from becoming failure or at least bound the effects of the fault and make repair possible. So that's how it works. The fault hits the tactics of control availability, and the fault mask or the repair mode switches on automatically. The availability tactics have detect faults, recover from faults, and prevent faults. If we look at this tree structure, the detect faults have ping, echo, monitor, heartbeat, timestamp, sanity checking, conditional monitoring, voting, exception detection, and self-test. Technically, that's how the availability tactics work. However, when recover from faults, it needs preparation and repair with active redundancy, passive redundancy, and the list goes on. And the reintroduction means shadow state resynchronization, escalating restart, and non-stop forwarding. So that means that the work that had been happening should commit once the availability tactics are taken care. To prevent faults is removal from the service. Transactions need to be stored in a safe way. Predictive model, exception prevention, and increase competence set. Detect faults. Ping or echo are asynchronous request response message pair exchanged between nodes used to determine reachability and the round trip delay through the associated network path. Monitor is a component used to monitor the state of health of other parts of the system. A system monitor can detect failure or congestion in the network or other shared resources, such as from a denial of service attack. The heartbeat is a periodic message exchange between the system monitor and a process being monitored. So we just have discussed that in the Techville University, how the system heartbeat actually woke up the IT support and get them fix the server. The detect fault continues timestamp used to detect incorrect sequences of events, primarily in distributed message passing systems. Sanity checking, where it checks the availability or reasonableness of a component's operation or outputs, typically based on a knowledge of the internal design, the state of system, or the nature of the information under scrutiny. The condition monitoring happens by checking the conditions in a process or device or validating assumptions made during the design. In voting, exception detection and self-test. In voting, to check that replicated components are producing the same results, comes in various flavors: replication, functional redundancy, analytic redundancy. Exception detection, where detection of a system condition that alters the normal flow of execution, such as system exception, parameter fence, parameter typing, and timeout. The self-test, where procedure for a component to test itself for a correct operation. Recover from faults, which is preparation and repair, as we discussed in the big picture. Let's look into this with the Techville University example. So since we are working with the city of Techville, the Techville University was a hub of innovation and learning. The university relied heavily on its digital infrastructure to manage everything from student records to online classes. At the heart of this infrastructure was a robust server system that ensured smooth operations. However, even the most well-designed system can encounter faults, and the IT department at Techville University was always prepared to handle such situations. One day during a routine check, the heartbeat monitor detected that the main server was non-responsive. This was a critical issue because the server hosted essential applications and databases that the entire university depended on. The IT team immediately received an alert from the monitoring system indicating a potential fault. They quickly assembled to diagnose the problem. The team started by checking the server's physical connections and power supply. Everything seemed to be in order, so they moved to examining the server logs. The logs revealed that there had been a sudden spike in traffic, which might have overwhelmed the server. To mitigate this, the team decided to temporarily redirect some of the traffic to the backup server while they worked on resolving the issue. With the immediate pressure of the main server, the IT team could focus on identifying the root cause of the fault. They discovered that recently installed software updates had introduced a bug that causes the server to become unresponsive under heavy load. The team quickly rolled back the update to the previous stable version of and began working on a patch to fix the bug. Once the patch was applied and tested, the main server was brought back online. The IT team closely monitored its performance to ensure that the issue was fully resolved. They also implemented additional safeguards to prevent similar incidents in the future. The university's operation returned to normal, and the IT department's swift action ensured that the impact on students and staff was minimal. This experience highlighted the importance of having a robust fault recovery plan in place to maintain the reliability of a critical system. If you're using Google Chrome or any other browser and you open, let's say, 70 windows, your system will significantly slow down. If out of 70 windows, even 5 windows are working non-stop, where you're running some videos or some streaming, you will see that your machine will have a degraded processing power at that time. So exception handling happens, dealing with the exceptions by reporting or handling it, potentially masking the fault by correcting the cause of the exception and retrying. Rollback is revert to the previous known good state, referred to as rollback line. Software upgrade happens in service upgrades to executable code images in a non-service affecting manner. So retry, when a failure is a transient retrying, the operation may lead to the success. Ignore faulty behavior, ignoring messages sent from a source when it is determined that those messages are spurious. Degradation maintains the most critical system functions in the presence of component failures, dropping less critical functions. Reconfiguration, reassigning responsibilities to the resources left functioning while maintaining as much functionality as possible. Shadow is operating a previously failed or in-service upgraded component in a shadow mode for a predefined time prior to the reverting the component back to an active role. The state resynchronization were partner to active redundancy and passive redundancy, where the state information is sent from active to standby components. Escalating restart recover from faults by varying the granularity of the components restarted and minimizing the level of service affected. Non-stop forwarding functionality is split into supervisory and data. If a supervisor fails, a router continues forwarding packets along known routes while protocol information is recovered and validated. To prevent faults is removal from service, temporarily placing a system component in an out of service state for the purpose of mitigating potential system failures. The transactions were bundling state updates so that asynchronous messages exchange between distributed components and atomic, consistent, isolated, and durable. So that is also known in databases: atomicity, consistency, isolation, and durability. The predictive model is monitor the state of health of a process to ensure that the system is operating within the nominal parameters. Take corrective actions when conditions are detected that are predictive likely future faults. Exception prevention happens when preventing system exceptions from occurring by masking a fault or preventing it via smart pointers, abstract data types, and wrappers. Increase competence set, designing a component to handle more cases fault as part of normal operations. Design checklist for availability. Let's look into this with an example. In the dynamic world of software architecture, ensuring the availability of systems is crucial for maintaining smooth operations and user satisfaction. One essential aspect of designing for availability is the allocation of responsibilities. This involves clearly defining who is accountable for various components and processes within the system, ensuring that everyone knows their role in keeping the system running efficiently. At Techville University, the IT department understood the importance of allocating responsibilities to enhance system availability. They began by identifying all the critical components of their infrastructure, such as servers, databases, network devices, and applications. For each component, they assigned a primary responsible individual or team. This person or team was tasked with monitoring the component's performance, addressing any issues that arose, and ensuring that it remained operational. To facilitate this process, the IT department created detailed responsibility matrix. This matrix outlined the specific duties of each team member, including routine maintenance tasks, emergency response protocols, and escalation procedures. For example, the server administration team was responsible for regular server health checks and applying security patches, while the network team handled connectivity issues and bandwidth management. Communication was the key to successful allocation of responsibilities. The IT department established clear communication channels and protocols to ensure that information flowed smoothly between teams. Regular meetings were held to discuss system performance, address any concerns, and plan for future improvements. This collaborative approach helped to identify potential issues early and prevented them from escalating into major problems. Moreover, the IT department implemented a robust training program to ensure that all team members were well equipped to handle their responsibilities. This individual technical training on specific systems and components, as well as soft skill training to enhance communication and problem-solving abilities. By investing in their team's development, the IT department fostered a culture of accountability and continuous improvement, ultimately enhancing the overall availability and reliability of the university systems. Now let's look into the coordination model in a little bit more depth. As we are working with the city of Techville, where Techville University's IT department was committed to maintaining a highest level of system availability. They understood that effective coordination among various teams and components was essential to achieve this goal. To facilitate this, they implemented a coordination model that outlined how different parts of the system would work together to ensure smooth operations. The coordination model at Techville University began with establishing clear lines of communication between teams. Each team, whether responsible for servers, databases, or applications, had designated points of contact. These individuals were tasked with facilitating communication and ensuring that information was shared promptly and accurately. Regular meetings were held to discuss system performance, upcoming changes, and any issues that needed to be addressed. This proactive approach helped to identify potential problems early and prevented them from escalating into major disruptions. One of the key aspects of the coordination model was the implementation and standardized process and protocols. These included incident response procedures, change management processes, and maintenance schedules. For example, when a server issue was detected, the incident response team followed the predefined protocol to diagnose and resolve the problem. This structured approach ensured that everyone knew their role and responsibilities, reducing confusion and expediting the resolution process. The IT department at Techville University leveraged technology to enhance coordination. They used collaboration tools and platforms to share information, track progress, and manage tasks. These tools provided real-time updates and allowed team members to communicate effectively, even when they were not physically in the same location. By embracing technology, the IT department was able to streamline their coordination efforts and improve overall system availability. Now let's look into the data model with an example. We'll continue with the Techville University in the city of Techville. At the heart of their digital infrastructure, the Techville University had a well-designated and designed data model, which played a crucial role in ensuring that availability and reliability of their systems are in context with the university needs. The data model served as a blueprint that defined how data was structured, stored, and accessed across the university's various applications and databases. The IT department at Techville University began by identifying the key entities involved in their operations, such as students, faculty, courses, and departments. For each entity, they defined a set of attributes that described its characteristics. For example, the student entity included attributes like student ID, name, major, and enrollment status. This structured approach ensured that the data was organized in a consistent and logical manner, making it easier to manage and retrieve. One of the primary goals of the data model was to establish relationships between different entities. For instance, a student could be enrolled in multiple courses, and each course was taught by one or more faculty members. By defining these relationships, the data model enabled the university to track and analyze complex interactions between entities. This was essential for processes like course registration, grade reporting, and faculty workload management. To ensure data integrity and availability, the IT department implemented strict data validation rules and access controls. These measures help to prevent errors and inconsistencies in the data, such as duplicate entities or incorrect values. Additionally, access controls ensured that the only authorized personnel could view or modify sensitive information, enhancing the security of the university's data. The data model also facilitated the integration of various systems and applications used across the university. By adhering to the common data structure, different departments could easily share and exchange information. This interoperability was crucial for maintaining the availability of services and ensuring that students and faculty had access to the information they needed when they needed it. Through careful planning and implementation, the data model at Techville University became a cornerstone of their digital infrastructure. supporting the university's mission to providing a seamless and enriching educational experience for everyone within the university system. Mapping among architectural elements determine which artifacts such as processors, communication channels, storage processes may produce a fault, omission, crash, incorrect timing, or incorrect response. Ensure that the mapping or remapping of architectural elements is flexible enough to permit the recovery from the fault. This may involve a consideration of which processes on failed processors need to be reassigned at runtime, which processors, data stores, or communication channels can be activated or reassigned at runtime, how data on failed processors or storage can be served by replacement units, how quickly the system can be reinstalled based on the units of delivery provided, how to reassign runtime elements to processors, communication channels, and data stores. When employing tactics, they depended on redundancy of functionality. The mapping from the modules to redundant components is important, such as it is possible to write a module that contains code appropriate for both the active and backup components in a protection group. Resource management. Determine the critical resources are necessary to continue operating in the presence of fault, omission, crash, incorrect timing, or incorrect response. Ensure that there are sufficient remaining resources in the event of fault to log the fault, notify appropriate entities, people, or systems, disable source of event causing the fault, fix or mask the fault failures, operate normally in startup, shutdown, repair mode, degraded operation, or overloaded operation. Determine the availability time for critical resources. What critical resources must be available during specified time interval. Time intervals during which the critical resources may be in a degraded mode, and repair time for critical resources. Ensure that the critical resources are available during these time intervals. For example, ensure that the input queues are large enough to buffer anticipated messages if a server fails to, so that the messages are not permanently lost. Binding time. Let's look into this with a running example. Let's continue the example of Techwell University, as it was at the forefront of integrating technology into its educational framework. We have established that context. One of the critical concepts the IT department focused on was binding time, which referred to the moment when different components of a system were connected or configured to work together. Understanding and managing binding time was essential for ensuring the system's availability and flexibility. The IT department at Techwell University recognized that binding time could occur at various stages of the system's life cycle. For instance, early binding happened during the design and development phase, where components were tightly integrated based on predefined specifications. This approach ensured that the system was robust and reliable from the outset, but offered less flexibility for future changes. In contrast, late binding occurred at runtime, permitting components to be connected dynamically based on current needs. This provided greater adaptability, enabling the system to evolve and incorporate new features or modifications without significant disruptions. To leverage the benefits of both early and late binding, the IT department adopted a hybrid approach. They used early binding for core system components that required high stability and performance, such as university's student information system. For other components like third-party applications or plugins, they opted for late binding. This strategy allowed the university to integrate new tools and service seamlessly, enhancing the overall user experience without compromising the system's integrity. Effective management of binding time also involved careful planning and coordination among different teams. The IT department established clear protocols for when and how components should be bound, ensuring that everyone understood their roles and responsibilities. Regular reviews and updates to the binding strategies help the university stay agile and responsive to changing the technological landscape and user needs. By mastering the concepts of binding time, Techville University assured that the systems remained available, adaptable, and efficient, supporting the university's mission of providing the cutting-edge educational environment. And the choice of technology: determine the available technologies that can help detect faults, recover from faults, reintroduce failed components. Determine what technologies are available that help the response to a fault, or even loggers. Determine the availability characteristics of chosen technologies themselves. What faults can they recover from? What faults might they introduce into the system? So let's summarize this lecture. Availability in software architecture refers to the ability of the system to be available for use when a fault occurs. The fault must be recognized or prevented, and then the system must respond. The response will depend on the criticality of the application and the type of fault. Can range from ignore it or keep on going as it is possible. The tactics for availability are categorized into detect faults, recover from faults, and prevent faults. Detection tactics depend on detecting signs of life from various components. Recovery tactics are retrying an operation or maintaining redundant data or computations. Prevention tactics depend on removing elements from service or limiting the scope of faults. All availability tactics involve the coordination model. Happy learning. See you in the next lecture.